In 2012, after 35 years of continuous flight, Voyager 1 crossed into interstellar space. The news went around the world. Headlines said it plainly. Humanity's farthest machine had left the solar system. People who had followed the mission for decades felt something real when they heard it. A genuine sense of threshold crossed, of boundary passed, of something accomplished that had never been accomplished before. But here is what those headlines did not say. By the gravitational definition of the solar system, the one most planetary scientists actually use when they are being precise. Voyager 1 has not left the solar system. It is not close to leaving it. At its current speed, travelling about 38,000 miles per hour without ever stopping. Voyager will need roughly 300 years just to reach the inner edge of a structure called the Oort Cloud. And after that, it will need approximately 30,000 years to cross through it completely. 300 years to reach the beginning of the edge. 30,000 years to cross it. Sit with those numbers for a moment. Not as facts to memorize. As a measurement of something you were never shown. There is a poster you have seen before. Maybe it was in a classroom when you were 8 years old. Maybe it was in a library. Or in a textbook that smelled like every other textbook on the shelf. The sun on one side, burning yellow and orange. Then the planets, lined up in a neat row moving outward. Mercury closest in. Then Venus. Then Earth. Then Mars. Then the giants. Jupiter with its stripes. Saturn with its rings. Uranus tilted on its side. Neptune at the far edge. Cold and blue and distant. You memorized that poster. Most people did. And somewhere in the process of memorizing it, something happened that nobody intended and nobody announced. The poster stopped being a simplified diagram and became, in the mind, the thing itself. The solar system as a flat row of objects with the sun at one end and darkness at the other. Contained. Knowable. Finished. That poster was not wrong. It was missing most of what it was supposed to show. Everything in that poster. Every planet. Every moon. Every ring system. Fits within the first 150 astronomical units or so from the Sun. The Oort Cloud, the structure that defines the solar system's true outer boundary, may extend to 100,000 astronomical units. 100,000 times the distance from the Earth to the Sun. The poster showed you less than 0.2% of the solar system's actual reach and called it the whole picture. Voyager 1 has been flying since the summer of 1977. It has travelled further than anything human beings have ever built. And it is still, by the measure of the solar system's true extent. In the front yard, if Voyager has entered interstellar space and still has not reached the Oort Cloud, then where does the solar system actually end? That question has an honest answer. The answer is going to require replacing a picture you have carried since childhood with something that does not fit on any classroom wall. The poster was the first page of a much longer story, and someone forgot to mention how many pages were left. Think about what the word neighbourhood means to you, not in the abstract, in the specific, physical, experience sense. A neighbourhood is a place you can walk through in an afternoon. It has edges you can reach. You know roughly where it ends and where the next thing begins. The corner store. The park 3 blocks over. The street where the houses start looking different and you realise you are somewhere else. A neighbourhood is human-scaled. It fits in the mind without effort. Most people carry the solar system that way. A neighbourhood with 8 addresses and one very bright lamp at the centre. The sun. The planets. Everything organised and named and containable. You can hold the whole thing in your head at once. You can draw it from memory. You know where it ends. It ends at Neptune. Except that it does not. Neptune sits about 30 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun. Roughly 93 million miles. So Neptune orbits at about 2.8 billion miles out. Light from the Sun takes over 4 hours to reach it. A spacecraft travelling at Voyager's speed would need about 12 years just to get there from Earth. By any ordinary standard, Neptune is remote. By the standard of the solar system's actual extent, Neptune is practically next door. Here is what the distances actually look like when you lay them all out honestly. Earth is at 1 astronomical unit. Mars is about 1.5. Jupiter is 5. Saturn is about 9.5. Uranus is 19. Neptune is 30. The poster feels like it is telling the truth. Then things change. The Kuiper Belt, the region of icy objects that begins just beyond Neptune, extends from about 30 astronomical units out to roughly 50. That is where Pluto lives, along with Eris and Makemake and thousands of other frozen objects. Past the Kuiper Belt, there is the scattered disk, where objects pushed by Neptune's gravity follow highly elongated orbits reaching into the hundreds of astronomical units. And then, beginning somewhere around 1,000 astronomical units from the Sun, the Oort Cloud begins. The inner boundary of the Oort Cloud is thought to start around 1,000 to 2,000 astronomical units. The outer boundary may extend to 100,000 astronomical units. Neptune is at 30. The Oort Cloud begins at 1,000. The Oort Cloud ends at 100,000. Here is how to feel that difference in a way that numbers alone cannot produce. If you put every planet in the solar system, every moon, every asteroid, every spacecraft humanity has ever launched, including Voyager, one after nearly 50 years of continuous flight, and you put all of it on one side of a scale, and put just the spatial extent of the Oort Cloud on the other side, the Oort Cloud would make the planetary solar system disappear into rounding error. The entire region of the solar system that the poster showed you, from the Sun to Neptune and everything in it, represents less than 0.2% of the solar system's actual radial reach. Think about the neighbourhood analogy one more time. If Neptune is the last house on your street, the Oort Cloud is not the next neighbourhood over. It is not the next town. It is somewhere on the other side of the state, in the dark, past the point where the roads have names and the lights from home are no longer visible behind you. And it is still, by the definition that most planetary scientists consider most physically meaningful, part of the same property, still held by the same sun's gravity, still part of the same solar system you were shown on the poster in 3rd grade. Neptune is not the wall. It is not the porch. It is not even the front steps. It is a lamp near the front door, warm and visible from inside the house, while the property extends far beyond the reach of its light in every direction. Everything humanity has ever launched has stayed very close to that lamp. The dark beyond it has barely been introduced. The question of why it took so long to understand the true scale of the solar system is worth asking for a moment. The answer is not complicated. We mapped what we could see. The planets are visible because they reflect enough light to be detected, because they move against the background stars in ways that ancient astronomers noticed without any technology at all. The Oort Cloud is invisible. Its individual objects are too small, too dark, and too far away to be detected directly by any telescope ever built. So for most of human history, the solar system looked like what the poster shows, not because anyone was wrong, but because the visible and the complete are not the same thing. It took a very specific kind of reasoning to figure out that there was more out there than anyone could see. But before getting to that reasoning, there is something worth understanding about why human beings kept drawing the border in the wrong place. Not because of bad science, because of something older and more fundamental than science. Something that has to do with how minds relate to the idea of home, and what happens when the edges of home turn out to be somewhere nobody expected. On August 24th, 2006, a room full of scientists in Prague voted on a question that should have been, by any reasonable measure, a quiet, technical matter. The International Astronomical Union had spent years debating what the word planet actually meant. As telescopes improved and surveys of the outer solar system became more systematic, it became clear that the object discovered in 1930 and called the 9th planet was not alone out there. It was one of many, Hundreds of similar objects orbited the Sun in the same general region, some of them nearly as large, at least one of them larger. The IAU decided to draw a cleaner line. A planet, under the new definition, had to orbit the Sun, had to be massive enough for gravity to pull it into a roughly spherical shape, and had to have cleared the neighbourhood around its orbit of other debris. The object in question met the first two conditions, but not the third. It was reclassified. The vote passed. The solar system officially had 8 planets. The object itself did not move. Its orbit did not change. Its moons were still there. Nothing about the physical thing in space was affected in any way by what happened in that conference room in Prague. The reaction from the American public was not quiet. Teachers wrote letters. State legislatures in New Mexico and Illinois passed resolutions declaring that it would always be considered a planet within their borders, as though orbital mechanics stopped at state lines. A campaign called Save Pluto circulated online before social media made those things routine. People who had not thought about astronomy in years suddenly had strong opinions about the classification of a frozen object billions of miles away. Late-night television hosts made jokes about it for weeks. Children learning the planets in school for the first time were genuinely upset in ways that surprised their parents. Why? That is the question worth sitting with. Not the scientific question of whether the reclassification was correct. The human question of why a change in a label, applied to an object that did not itself change in any way, produced that kind of response. The answer is that what people mourned was not the object. It was the border. Pluto was the last name on a list, the final entry in a sequence that had a beginning and a middle and an end. The solar system, as most people had learnt it, was a story with 9 chapters. The first chapter was Mercury. The last chapter was Pluto. And when you finished the 9th chapter, the story was over and you knew where you stood. You were at the edge. Beyond Pluto was not the solar system anymore. Beyond Pluto was just space. The vast, undifferentiated dark that was not home and not ours and not part of the picture. When the IAU reclassified that object, it did not just change a category. It removed the last page of a story that a lot of people had been reading since childhood. And when the last page disappears, you do not know where the story ends. The edge, which had always been right there at the end of the list, suddenly was not where you thought it was. That is not a scientific feeling. That is an ancient human feeling. The feeling of a boundary dissolving. Human beings draw borders. This is not a flaw. It is a feature of minds that need to organize a world too large and too complex to hold in full. Every map ever made is a border drawing exercise. Every category. Every name applied to a type of thing, rather than an individual thing, is a border drawn between this and not this, here and not here, home and somewhere else. The borders are useful. They allow navigation. They allow the kind of shared understanding that makes it possible for people to talk about the solar system without spending an hour defining terms every time. But there is a difference between a border that describes something real in nature and a border that describes something real only in the mind. The coastline of a continent is a border of the first kind. The atoms do not care where you draw the line between land and water. But there is a genuine physical transition there that the border is trying to describe. The category of planet, it turned out, was a border of the second kind. Nature did not draw a line between planets and non-planets. Nature produced a continuous distribution of objects ranging from tiny specks of dust to worlds larger than Earth, orbiting the Sun at every distance and in every configuration. The line between planet and not planet was drawn by human beings trying to make sense of that continuous distribution. And when the line was redrawn in 2006, the emotional response revealed how deeply people had mistaken the human-drawn line for a natural one. This matters for understanding the Oort Cloud, because the same mistake runs through almost every popular idea of where the solar system ends. When people say the solar system ends at the last planet, they are not reporting a fact about nature. They are reporting the location of a border that was drawn for convenience. Because the last planet is the last thing with a name that most people know. the last address on the street before the unfamiliar begins. The border feels real because it has been repeated so often, but it is not where nature draws the line. Nature does not draw lines. This is perhaps the most important thing to understand about the outer solar system, and it is also the hardest. Because minds built for border drawing find it genuinely uncomfortable to sit with gradients and transitions and regions where one thing slowly becomes another thing without any announcement. The sun's gravity does not stop at the last planet. It does not stop at the Kuiper Belt. It does not stop at the heliopause. Where the solar wind meets the interstellar medium and Voyager crossed into what the headlines called interstellar space, the sun's gravity extends outward continuously, weakening with distance, yielding gradually to the gravity of other stars and the collective pull of the galaxy, but never dropping to zero at any specific, identifiable, nameable location. The edge of the solar system is not a place. It is a process, a slow yielding of the sun's authority over an enormous region of space, a gradual transition from here to somewhere else that plays out over tens of thousands of astronomical units. There is no wall, there is no sign, there is no moment of crossing from inside to outside the way Voyager's instruments detected a crossing of the heliopause. What there is, out in the dark, past everything the poster showed, is the Oort Cloud, a structure so large that calling it part of the solar system feels almost like a category error, because the solar system, as most people conceive of it, is a much smaller and tidier thing than what the Oort Cloud actually is. And yet the Oort Cloud is the solar system, the real solar system, the full extent of what the sun holds and has held for 4.5 billion years. The border at the last planet was a convenience. The actual edge of the solar system, to the extent that one exists, is somewhere out in a darkness that no probe has reached and no telescope has photographed, in a region that most people who learn the poster by heart have never had occasion to think about at all. Understanding why we drew the wrong border is the first step toward understanding where the right one might be. The second step is going to the shoreline, standing at the edge of the familiar and looking out at what comes next. Because what comes next is not nothing. It is the beginning of something so large that the word large is not quite adequate. And getting there requires travelling through a region of the solar system that most people know only by a single name. A name that for decades stood as the border itself before science moved the border and the public had not quite finished grieving. Step outside the last familiar thing, past Neptune, past the orbital paths of everything with a name that most people recognise. You are now entering the Kuiper Belt, and the first thing you notice, if noticing were possible out there, is that the light is wrong. The sun is still the brightest object in the sky by a significant margin. You can find it without difficulty, but it does not look like the sun you know from Earth. At 30 to 50 astronomical units from the sun, the light that reaches you has been travelling for 4 to 7 hours. It arrives roughly 1,000 times fainter than what you experience on a clear afternoon. The sun at that distance is a very bright star, brilliant enough to cast faint shadows, but not warm, not in any way that matters to anything alive. There is no warmth in the Kuiper Belt. The surfaces of objects out there hover somewhere around 40 to 50 Kelvin, which is roughly 220 degrees below 0 Fahrenheit. The kind of cold where familiar chemistry stops working, where gases that flow freely on Earth are frozen into crystalline solids, where the concept of a liquid does not apply to anything in the environment. Pluto is the most famous resident of this region. For most of the decades since its discovery in 1930, it was also the least understood. A small bright dot in telescope images, its surface unknown, its internal structure guessed at. Then, in 2015, the New Horizons spacecraft completed a journey of 9 years and 3 billion miles and flew past Pluto at a distance of about 7,500 miles. And for the first time, human beings saw what Pluto actually looked like. What they saw was not what most people expected. Pluto has mountains, genuine mountains, peaks of water ice rising up to 11,000 feet above the surrounding terrain, comparable in height to the Rocky Mountains. It has a vast, smooth plain of frozen nitrogen the size of Texas, so flat and featureless that geologists concluded active processes had resurfaced it relatively recently. It has a thin atmosphere of nitrogen, methane, and carbon monoxide that expands when Pluto swings closer to the Sun and contracts when it moves away. It has 5 known moons, the largest of which, Charon, is so large relative to Pluto that the two orbit a shared centre of gravity located in the space between them rather than inside either body. Pluto is not a dead, featureless ball. It is a genuinely complex world, shaped by geological processes nobody fully anticipated, and it is one of hundreds of thousands of similar objects in the Kuiper Belt, Eris, Makemake, Haumea, thousands more without names, following slow orbits in the same frozen region, each one a world in its own right, and each one almost entirely unknown, most just sitting there, cold and dark and old, in orbits that carry them around the Sun so slowly that a single year on, many of them last longer than all of recorded human civilization. Objects in the Kuiper Belt, remnants of the outer disk whose orbits were shaped by Neptune's gravity during the early solar system, can be pushed onto trajectories that eventually bring them closer to the Sun. As they warm up during that inward journey, their ices sublimate and the gas and dust that escape form the tail and coma we see from Earth. These are the comets with orbital periods of a few years or a few decades, the ones that return on schedules astronomers can predict. But the Kuiper Belt is not the edge. Stand on the shore of any ocean and look out. The water in front of you is real. The distance is real, but the shore is not where the ocean begins. It is where the land ends. The ocean was already there, extending further than the eye can follow, long before you arrive to look at it. The Kuiper Belt is that shore. Beyond it, the water goes deeper than any map has ever measured. The light from the Sun continues to fall, fainter and fainter, over distances that the poster never suggested and the imagination struggles to hold. And somewhere out there, in the dark past the shoreline, something enormous has been waiting for 4.5 billion years. Not waiting the way something with intention waits, just existing, in a silence that has no comparison anywhere on Earth. In the Kuiper Belt, the Sun is still the Sun, faint and cold, yes, but still identifiable as the source. Still dominant in the sky. Still the reason the surfaces of these objects are slightly warmer than the universe's background temperature. Out past the Kuiper Belt, even that faint dominance begins to fade. The transition is not dramatic. There is no moment when a traveller would stop and say, "Here, this is where the Sun stopped mattering." It just fades, the way a voice fades when the person speaking it walks slowly away, until you are not sure whether you can still hear it or whether you are just remembering the sound. A man named Jan Oort glimpsed the outline of what lies beyond that fading in 1950. He did it without leaving his desk. He did it with 19 comets and a sheet of calculations and a question that nobody else had thought to ask quite the way he asked it. He did not have a telescope powerful enough to see what he was describing. He did not need one. That is the next part of the story. Leiden is a small city in the western Netherlands, about 25 miles southwest of Amsterdam, built along a network of canals that branch off from the Rhine. It has a university that dates to 1575, one of the oldest in Europe, founded as a reward to the city's citizens for their resistance during a siege. Over the centuries, the university produced an unusual number of significant scientists. By 1950, the Leiden Observatory was one of the leading centres of astronomical research in the world. Jan Oort had been there for most of his professional life. Born in 1892 in the Dutch town of Franeker, he had come to Leiden as a student and stayed as a researcher, eventually becoming director of the observatory. By 1950, he was 58 years old and had already done work that placed him among the most significant astronomers of the 20th century. In the 1920s, he had provided crucial evidence that the Milky Way galaxy rotates. and had estimated the Sun's distance from the galactic centre with a precision that later measurements confirmed was remarkably accurate. He was not a man given to dramatic announcements. He was a man given to data. In 1950 he turned his attention to comets. Not to any specific comet, to the population of comets as a whole, and to a question that had been sitting at the edge of solar system science without a satisfying answer for a long time. The question was simple to state and surprisingly difficult to answer. Where do long-period comets come from? A long-period comet is a comet with an orbital period longer than 200 years. Some have periods measured in thousands of years, some in millions. Some appear to be making their very first approach to the inner solar system, arriving on orbits so elongated that they will not return for timescales that exceed the current age of the Earth. They arrive from every direction, not just from the plane in which the planets orbit, but from above and below it, from every angle imaginable. And they come from very, very far away. This directional randomness was the key observation. If long-period comets came from a flat belt, like the Kuiper Belt, they would arrive preferentially from directions near the plane of the solar system. The fact that they arrive from all directions equally, from the full sphere of the sky, meant their source had to be spherical, not a ring, not a disk, a shell, something surrounding the solar system equally in every direction. Oort collected orbital data for 19 long-period comets. He calculated the aphelion distances for each of them, the farthest points from the Sun in their orbits, the places where each comet had spent most of its existence before something sent it falling inward. The numbers he calculated were staggering. The origin points clustered around 50,000 astronomical units, not randomly scattered, clustered. In a pattern too tight to be coincidence, something was out there at roughly 50,000 astronomical units. Not a single object, but a reservoir, a vast population of objects in stable orbits at that distance, from which individual members were occasionally knocked loose and sent falling inward toward the Sun. And the knocking mechanism, Oort proposed, was passing stars, other stars moving through the galaxy on their own independent orbits, occasionally passing close enough to the Sun to gravitationally nudge objects at the outermost edge of the Sun's influence, sending them onto new trajectories that eventually brought them across the inner solar system as comets. He had never seen this reservoir. He could not see it. No telescope available in 1950, and no telescope available today, has the sensitivity to directly detect individual Oort Cloud objects at their actual distances. They are too small, too dark, and too far away. A typical Oort Cloud object, a few miles across with a surface that reflects almost no light, sitting at 50,000 astronomical units from the Sun, produces a signal that falls far below the detection threshold of any instrument ever built. What Oort saw was the shadow of the thing, the shadow it cast on the distribution of comet orbits, the way a large spherical distant reservoir of icy objects would produce exactly the population of long-period comets that astronomers had been observing and cataloguing for centuries without understanding where they came from. Here is the sharpest way to describe what he did. Imagine you are standing in a completely dark room. Someone tells you there is a large object in the room with you. You cannot see it. You cannot touch it. But occasionally, from somewhere in the dark, a small piece of something rolls across the floor toward you. You watch where those pieces come from. If they roll toward you from every direction equally, from your left and your right and from behind and from above, you know the object is not a flat disk leaning against one wall. It is surrounding you. It is a sphere. You have just figured out the shape of something you cannot see, using only the paths of the pieces it occasionally sends your way. That is what Jan Oort did. In 1950, with 19 comets, in a room in the Netherlands, the structure he described acquired his name, the Oort Cloud. In the 74 years since that paper was published, every additional long-period comet that has been tracked and measured, every theoretical model of how the outer solar system formed and evolved, Every study of how passing stars and galactic tides interact with the outermost reaches of the Sun's gravitational domain has added weight to his basic framework rather than undermining it. The details have been refined. The estimates of the cloud's inner and outer boundaries have shifted as models improved, but the core of what he said has held up against 74 years of increasingly sophisticated scrutiny. Oort named something he could not see. 74 years later, we still cannot see it. The comets have not stopped pointing back toward the dark, he named. There is a particular kind of scientific achievement that does not get the recognition it deserves because it lacks the drama of discovery in the conventional sense. Nobody looked through a telescope and gasped. Nobody saw a new object appear in a field of stars. Oort sat at a desk in Leiden and thought carefully about a pattern in some numbers and described something the size of a light year that was hiding in plain sight behind the veil of distance and darkness. The telescope reveals what is there to be seen. The mind, working on the shadows that invisible things cast on visible ones, reveals what is there to be known. Oort used the second tool, and what he found with it was the largest structure in the solar system, described from a desk, with 19 data points, in a city built on canals, in the middle of a century that had not yet figured out how large the home it was living in actually was. Everything you have ever been shown when someone says solar system is flat. The poster is flat. The animated diagrams in science documentaries are flat. The model sitting on the shelf in the science classroom, plastic planets on wire orbits around a yellow foam sun, is flat. Even the mental image most people carry without thinking about it, the one that appears automatically when someone says solar system, is flat. A disk, a plane, everything radiating outward from a central point in the same two-dimensional sweep, the way ripples spread from a stone dropped in still water. This flatness is not an artistic choice or a simplification made for the sake of classroom clarity. It reflects something real about the inner solar system. The planets do orbit close to a common plane. They formed from a spinning disk of gas and dust that surrounded the young sun 4.5 billion years ago, and the physics of that spinning disk flattened everything into a shared plane, the way a spinning ball of dough flattens when you work it. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, all of them orbit within a few degrees of the same plane, the one astronomers call the ecliptic. The Kuiper Belt is also roughly disc-shaped, its objects orbiting in the same general plane as the planets, spread over a broader range of inclinations but still recognizably disc-like in their overall distribution. The flat picture is accurate for the planetary solar system. The problem is that the planetary solar system is not the whole solar system. Jan Oort knew this in 1950 from the directional distribution of long-period comets. They came from every direction equally, from above the ecliptic and below it and at every angle in between. A flat disc-shaped source would produce comets arriving mostly from the plane. A spherical source would produce comets arriving equally from every direction. The comets arrived equally from every direction. Therefore the source was spherical. The Oort cloud is not a disk. It is a shell. A thick, roughly spherical region of space surrounding the entire solar system. The planets, the asteroid belt, the Kuiper Belt, all of it, in the way that an atmosphere surrounds a planet. Objects in the Oort cloud orbit the Sun at every inclination and in every direction. Some orbit in the same direction as the planets. Some orbit in the opposite direction. Some orbit nearly perpendicular to the plane of the planets, their paths looping far above and below the ecliptic in enormous ellipses. There is no preferred direction. There is no up or down in the Oort cloud in the sense that up and down are defined by the ecliptic in the inner solar system. This is the moment when the childhood diagram stops being useful. Not just incomplete the way the poster is incomplete because it leaves out the Kuiper Belt. Fundamentally misleading about the shape of the thing it is trying to describe. Here is the image that holds this best. Imagine a single candle burning in the center of a completely dark room. The candle throws light in every direction. Close to the candle, the light is bright enough to read by. Halfway across the room, you can still see clearly. Near the walls, the light is dim, barely enough to make out shapes. At the walls themselves, the light is so faint that you might question whether it is reaching you at all. But the candle is still the reason there is any light in the room at all. And the room itself, every cubic foot of it from the candle to the walls, is defined by the relationship between the light source at the center and the space it reaches. The sun is the candle. The inner solar system, where the planets live, is the bright circle immediately around it, warm and lit and full of the complex activity that proximity to the candle makes possible. The Kuiper Belt is the middle distance, where the light is still present but noticeably dimmer, and the warmth has faded into something that instruments can measure but nothing alive could feel. The Oort Cloud is the walls of the room, barely lit, cold, almost completely dark, but still part of the same space defined by the same source. The room is spherical. The candle illuminates it equally in every direction, and the walls are very, very far from the candle. Now, here is what makes that image land differently than it might seem at first. The disk of the planetary solar system, including the Kuiper Belt, extends to roughly 50 astronomical units across its plane. Think of that as a coin. The Oort Cloud forms a sphere around that coin with a radius of up to 100,000 astronomical units. The coin sits at the center of a sphere whose radius is 2,000 times the coin's own radius. To hold that comparison in physical terms, if you are holding a quarter between your fingers right now, the Oort Cloud at that scale would form a sphere extending about 30 feet in every direction from where you are standing. The quarter, with all 8 planets, all their moons, all the asteroids, all the Kuiper Belt objects, all the spacecraft humanity has ever built, would be suspended at the center of a sphere so large that you could not touch any part of its surface from where you are standing. And that sphere would be almost entirely empty. Not empty in the way everyday spaces are empty, but empty in the astronomical sense, where even hundreds of billions of objects separated by tens of millions of miles amounts to one of the most diffuse structures in the known universe. The shape change matters as much as the scale change. When the solar system was a disk, it was a thing you could travel across in one direction. You could move from the sun outward along the plane and eventually reach the edge. The journey had a direction and a destination. When the solar system becomes a sphere, the geometry changes completely. There is no single edge in one direction. There is an edge in every direction simultaneously, at an equal distance, no matter which way you go, surrounding the center rather than terminating it. Earth sits near the center of that sphere, not at the exact center. The sun is at the gravitational center, but near it, vastly closer to the center than to any edge. The edge of the solar system is roughly 100,000 astronomical units from the sun in every direction. Earth is 1 astronomical unit from the sun. In every direction you point, up, down, sideways, toward where Neptune orbits or straight up through the plane or anywhere else. The solar system extends equally far. We are not near the edge. We have never been near the edge. 3-3, we live very close to the center, gathered around the candle, inside a room whose walls we have never seen, and whose full size we are only now beginning to measure. The solar system does not end as a line. It ends as a sphere. And that sphere is so large that everything we have ever thought of as the solar system, every planet, every moon, every asteroid, every spacecraft, fits inside a small, bright region near its center. The classroom diagram was a floor plan that forgot to include the walls, the ceiling, and the vast dark property between the house and the edge of the land. And now that the shape is clear, the question that follows is the one that tends to stop people for a moment longer than they expect. How big is this sphere? Actually, not in astronomical units, not in light years, in the only scale that human beings have ever really been able to spend, in time, in history, In the distance between now and when? In the summer of 1977, the United States was a country still finding its footing after one of the more turbulent decades in its history. A new president named Jimmy Carter had moved into the White House that January. In movie theaters across the country, a film called Star Wars had opened in May and was still selling out shows 4 months later. Lines wrapping around the block in cities from New York to Los Angeles. The country was in a particular mood. A mixture of weariness and the tentative beginnings of something that felt like forward motion again. That summer, NASA did something that would turn out to be one of the most consequential acts in the history of human exploration, though it did not feel that way at the time. On August 20th, Voyager 2 lifted off from Cape Canaveral. On September 5th, Voyager 1 followed. They were built to last 5 years. They were aimed at the outer planets, with the possibility of continuing on to Uranus and Neptune if everything held together. The outer planets were in an alignment that would not recur for another 175 years. A gravitational geometry that would allow a single spacecraft to use each planet's gravity to slingshot toward the next. Nobody seriously expected the spacecraft to still be operating nearly 50 years later. They are still operating. Voyager 1 is the most distant human-made object in existence. It has been travelling continuously since September of 1977, covering about 38,000 miles per hour, which works out to roughly 1 million miles every day. In 2012, after 35 years of uninterrupted flight, it crossed the heliopause and entered what scientists call interstellar space. The signal confirming this crossing travelled back to Earth at the speed of light and still took more than 17 hours to arrive. By any ordinary standard, Voyager 1 is incomprehensibly far away. By the standard of the Oort Cloud, it has barely left the neighbourhood. At its current speed, Voyager 1 will reach the inner edge of the Oort Cloud in approximately 300 years. Not 300 days. 300 years from now. To put that in terms of American history, 300 years ago was the early 1700s. Before the United States existed as a country. Before the Constitution was written. Before George Washington was born. Every president, every war, every invention, every cultural shift in all of American history fits inside the span of time that Voyager will spend travelling from where it is now to where the Oort Cloud begins. And reaching the inner edge is not crossing the Oort Cloud. That is just arriving at the doorstep. To travel through the Oort Cloud completely, from its inner boundary to its outer edge and out the other side, Voyager would need approximately 30,000 years at its current speed. 30,000 years ago, human beings were living in small groups in the Paleolithic world, long before agriculture existed, long before the first city was built, long before writing was invented. Everything that has happened in all of recorded human history, every civilization that rose and collapsed, every language born and forgotten, every war fought and every peace signed, every book written and every cathedral built, all of it fits inside 1/6 of the time it would take Voyager to cross the Oort Cloud. That is not a metaphor. That is the actual geometry of the place we live. Here is the comparison that makes this feel real in the body rather than just in the mind. Imagine you are standing in a field and you take one step. That step represents the distance from the Earth to the Sun, about 93 million miles. At that scale, each step is one astronomical unit. Mercury is less than half a step away. Venus is about 7/10 of a step. Mars is 1.5 steps. Jupiter is 5 steps away. You are still standing in the same part of the field. Saturn is 9.5 steps. Uranus is 19. Neptune is 30 steps away. You could reach Neptune, at that scale, in about 30 seconds of walking. The heliopause, where Voyager crossed into interstellar space in 2012, is about 120 steps away. A short walk, maybe 2 minutes. The inner edge of the Oort Cloud is roughly 2,000 steps away. That is about 1.5 miles. You left the field a while back. You have walked into another part of town entirely. The outer edge of the Oort Cloud is 100,000 steps away. At a normal walking pace, that is a journey of about 57 miles. If you started at the sun and walked toward the outer Oort Cloud, you would be walking all day. You would cross multiple counties. You would need to stop for the night and continue in the morning. And here is the part that changes everything about the walk. Every planet in the solar system, every moon, every asteroid, every Kuiper Belt object, every spacecraft humanity has ever built, including Voyager 1, after nearly 50 years of continuous flight. All of it sits within the first 200 steps of that 57-mile journey, about a tenth of a mile, a distance you could walk in under 2 minutes. The remaining 56 and 9/10 miles belong to the Oort Cloud, cold, dark, invisible, unvisited by anything human beings have made or will make in any time frame that any living institution can meaningfully plan toward. Voyager 1, the machine that humanity sent further than anything we have ever sent. The probe that crossed into interstellar space and sent back signals that took 17 hours to arrive at the speed of light, is somewhere in those first 200 steps. After nearly 50 years of flight, it is still, by the measure of the solar system's true extent, in the front yard. The reason for dwelling on this is not to diminish what Voyager has accomplished. Voyager is extraordinary. It was designed to last 5 years and has lasted nearly 50. It is still transmitting. The people who built it and tracked it across 5 decades have done something that deserves to be called remarkable without any qualification. But Voyager reveals something that human achievement, as extraordinary as it is, cannot change. The universe is not scaled to our effort. It is scaled to something else entirely. And the Oort Cloud sits at a distance that does not register human endeavour as meaningful in any way. It sits where it sits, because that is where the sun's gravity placed the material that accumulated there 4.5 billion years ago. It will still be sitting there, in that same vast dark sphere, long after Voyager's power sources have finally gone quiet, and the spacecraft becomes just another piece of matter moving through the dark at 1,000,000 miles a day, with no signal left to send and no one left to hear it. Voyager is not at the edge. It is still on the long road to the beginning of the edge. We sent the farthest thing we have ever made into the dark, and it is still, by the measures that matter most, very close to home. The Oort Cloud contains, by the best estimates that current science can produce, somewhere between several 100 billion and several trillion individual objects. That range is wide, and it carries significant uncertainty in both directions. Because nobody has counted them, nobody can count them. No telescope ever built, and no telescope currently planned or funded, has the combination of light-gathering power and sensitivity needed to detect individual Oort Cloud objects at their actual distances. They are too small, too dark, and too far away. What we have instead of a direct count is a chain of inference. How many long-period comets arrive in the inner solar system per year? How efficiently are those comets launched from the cloud by stellar perturbations and galactic tides? How many source objects must exist out there to sustain the observed arrival rate over billions of years? Given that each dislodged comet is either destroyed by repeated close approaches to the Sun or ejected from the solar system entirely after a few orbits. Working backward through that chain of reasoning produces the estimate of hundreds of billions to 1 trillion objects or more. But the chain has real uncertainties at every link, and the true number could be meaningfully different from any single figure. What the estimates do agree on is that even with hundreds of billions of objects, the Oort Cloud is almost empty. This sounds like a contradiction, and in human terms it almost is. The Oort Cloud occupies a volume of space so vast that even 1 trillion objects, each separated from its nearest neighbour by distances measured in tens of millions of miles, amounts to one of the most diffuse structures in the known universe. If you were somehow transported to the middle of the Oort Cloud and placed on the surface of one of its objects, You would look out at a sky full of stars and see almost nothing nearby. No neighbouring object visible to the naked eye. No sense of being in a crowd or even a sparse population. Just the stars, distributed across the sky with the same density they have everywhere in this part of the galaxy, and the faint bright point of the sun in one particular direction, and nothing else. The objects themselves are not dramatic things. Most of them are small, probably a few miles across at most, though some are certainly larger. They are dark, absorbing nearly all the faint sunlight that reaches them and reflecting almost none of it back. Their surfaces are coated in a mixture of water, ice, frozen carbon dioxide, frozen methane, frozen ammonia, and organic compounds formed over billions of years of exposure to cosmic radiation. That slow radiation processing, operating over 4.5 billion years, converts simple ices into more complex organic material, likely giving many of them dark reddish surfaces in the outer cloud. Far from any significant source of heat, the surface temperature of a typical object may be somewhere between 4 and 10 Kelvin. Absolute zero is 0 Kelvin, the coldest temperature that physics allows. The coldest air temperature ever recorded on Earth's surface was measured at a Russian research station in Antarctica, at about minus 129 degrees Fahrenheit. A typical Oort cloud object is hundreds of degrees colder than that. The comparison almost stops being meaningful. Earth's coldest air is still warm compared with the outer Oort cloud. At those temperatures, chemistry as it occurs on Earth does not happen. Everything is locked. Everything is still. The objects in the Oort cloud are not merely old. They are primordial, remnants of the disk of gas and dust that surrounded the young sun 4.5 billion years ago, before the planets had fully formed, before Earth had oceans, before anything on this planet had learned to replicate itself. In the early solar system, as Jupiter and Saturn grew massive enough to throw their gravitational weight around, they scattered enormous quantities of icy material outward from the forming planetary region. Some of that material was ejected completely from the solar system, flung out with enough velocity to escape the sun's gravity entirely and begin a journey through the galaxy with no destination. Some was caught at enormous distance by the combined influence of the sun's gravity, passing stars, and the gravitational pull of the galaxy itself, and settled into the slow, vast orbits of the Oort cloud. They have been there ever since. 4.5 billion years is a number that resists full comprehension. So consider it this way. They were there before the first eye opened on Earth, before any living thing on this planet had developed the structures needed to see. They were there when the dinosaurs ruled every continent, filling 165 million years of evolutionary time with a diversity of life that dwarfs anything the age of mammals has produced. They were there when the asteroid hit 66 million years ago and ended that era in fire and darkness and a winter that lasted years. They were there when the first human beings looked up at the night sky and wondered what they were looking at. Nothing about them has changed through any of this. Not their composition, not their orbits in any meaningful way, not the silence they inhabit. They have continued their slow circuits around a sun they have never approached closely, in a darkness so complete that the concept of silence on Earth, where there is always air and always vibration and always some sound moving through the medium around you, is only an approximation of what silence actually means out there. They carry in their composition and structure the chemistry of the outer solar system as it existed before any planet had fully formed. They are the raw material of a solar system that had not yet decided what it was going to become, preserved in the cold, the way nothing on Earth's active, volcanic, tectonically restless surface could ever be preserved. Right now, as everything on Earth moves and changes and speaks and builds and forgets, hundreds of billions of frozen objects are continuing those slow circuits. They do not know they are part of a solar system. They do not know anything at all. They are just old and dark and enduring, which, in the outer reaches of space, turns out to be enough. There is something clarifying about that. If you let it land, The Oort Cloud is not waiting for us to visit it. It is not waiting for anything. It was there before we existed and will be there after everything we have built has become something else. Its patience is not a virtue because it has no awareness of time. It is simply the oldest neighbourhood in the solar system, preserved exactly as it was at the beginning, in a cold and darkness so complete that 4.5 billion years have passed without leaving a mark. The comets that fall inward from that reservoir are the only messages it sends, the only way it announces itself to the inner solar system, the only evidence that arrives at our doorstep from the dark. Those messages are the next part of the story. Something is moving right now, not metaphorically. At this actual moment, in a region of space so far from the sun that the sun itself has become just another point of light in the sky. A body of ice that has not moved significantly in 4 billion years is beginning to shift. The change is almost nothing by any measure a human instrument could detect at that distance. A tiny alteration in velocity, a nudge so slight that expressing it in miles per hour would require more decimal places than the number would be worth writing. The object has been following the same path around the sun since before the Earth had continents, and this change will not visibly alter that path for thousands of years, but it is enough. In the mathematics of orbital mechanics, small forces applied over long times produce large effects. What is happening right now, invisibly, at a distance that makes Voyager's current position look like the end of the driveway, is the beginning of a journey that will eventually produce one of the most spectacular things a human being can see with the naked eye from the surface of Earth. The cause of the nudge is a star, not a dramatic close encounter, not a near collision, just a star pursuing its own orbit through the Milky Way, passing within a light year or two of the Sun over a period of hundreds of thousands of years, close enough that its gravity reaches out and touches the most loosely held objects at the solar system's outer boundary. The star does not know it is doing this. What is happening is physics, patient and indifferent, doing what physics does across timescales that have no human equivalent. The nudge changes the object's orbit by an amount that would be invisible even if you were watching from nearby. But the change is cumulative. Over the next 100,000 years, the orbit will shift. The path that has kept this object at a relatively stable distance from the Sun will begin to tilt inward. The closest point of approach, which has been tens of thousands of astronomical units, will begin to decrease. Slowly at first, then faster as the geometry of the orbit changes and the Sun's pull begins to dominate more and more of the object's motion. The object will fall inward, toward the centre of the solar system, toward the warmth it has never experienced in 4.5 billion years of existence. The fall will take millions of years. There is no way to make that number smaller or more digestible. Millions of years is the unit in which this journey is measured. The object will spend most of that time in the outer Oort Cloud, where the Sun's pull is still so weak that even substantial changes in orbit play out at a pace that makes glaciers look impulsive. It will cross the boundary between the outer and inner Oort Cloud over a period longer than the time since the dinosaurs went extinct. It will spend more time crossing the emptiness between the Oort Cloud and the Kuiper Belt than all of recorded human history multiplied by 1,000. But it will keep falling. The laws of gravity do not have a patience threshold. The pull is constant, and constant pull produces constant acceleration, and constant acceleration over millions of years produces a velocity that begins to feel like speed, even by the standards of inner solar system dynamics. By the time the object crosses Neptune's orbit, something begins to happen that has never happened to it before in its existence. The Sun is getting closer, not just cosmically closer, physically closer in a way that begins to matter. The surface temperature begins to rise. Not quickly, not all at once, but the frozen volatiles that have been locked in crystalline structures since the solar system's earliest years are sensitive to even small changes in temperature. Water ice begins to sublimate at the outer layers. Carbon monoxide, which sublimates at temperatures far below water, begins to come off even sooner, producing the first thin envelope of gas around the nucleus. The coma begins to form. a cloud of gas and dust expanding outward in all directions. Swept back by the pressure of sunlight and the solar wind into the distinctive shape that human beings have been staring at and drawing and writing about for as long as there have been human beings doing any of those things. The tail forms. 2 tails. Actually, one made of dust, curving gently along the arc of the orbit, reflecting sunlight in a pale, continuous stream. One made of ions, electrically charged particles pushed directly away from the sun regardless of the comet's direction of travel, pointing straight back like a flag in a wind that blows outward from the centre of the solar system without stopping. Together they can stretch for tens of millions of miles from Earth. Someone will look up. They will not know, in the full sense, what they are seeing. They will see a comet, bright or faint, depending on how close the object comes to the sun and to Earth, moving slowly against the background stars over days and weeks. If they are astronomers, they will measure its spectrum and calculate its orbit. The orbit will be extraordinary. The period will be millions of years. The origin will trace back to the outer Oort Cloud. They will call it dynamically new, meaning it appears to be entering the inner solar system for the first time. They will be right. This particular object has never been close to the sun before. Not once in 4.5 billion years. The warmth it is experiencing for the first time, the solar radiation liberating its gases and creating the display that someone on Earth is watching, is genuinely the first time this has happened to this object. It came a very long way for a few weeks in the inner solar system. Human beings have been watching comets for as long as there have been human beings capable of organized observation. Chinese astronomers kept detailed records of comet appearances going back at least 2,000 years, noting their positions, their brightness, the length and direction of their tails. Ancient Greek philosophers debated whether comets were atmospheric phenomena or genuine celestial objects. In medieval Europe, comets were read as omens, signs of plague or war or the death of kings. The appearance of a bright comet was treated as a message from somewhere beyond the ordinary sky, a disruption of the expected order of things, a sign that something significant was either coming or had already arrived. That instinct was not entirely wrong. Something significant was happening when a comet appeared. A piece of the outer solar system was making a crossing into the inner one, a frozen relic of the earlier solar system, travelling for millions of years, was arriving in the sky of a planet that had been through 500 million generations of life since the object began its fall. The people who looked up and felt that something unusual was happening were not misreading the situation. They were just missing the scale of it. The something coming from beyond the ordinary sky was real. It was just older and further away than any human cosmology had the tools to imagine. Some comets, the short-period ones with orbital periods of a few decades, are well-known visitors. They come back. Their returns are predicted. Halley's Comet, orbiting on a roughly 75 to 76-year cycle, has been watched and recorded by human beings across dozens of its returns. A reliable if infrequent presence in recorded history. Long-period comets from the Oort Cloud are different. Their orbital periods are measured in millions of years. When one appears in Earth's sky, nobody alive has ever seen it before. Nobody who will ever live will see it again. It is a one-time visitor from a region of the solar system that no human probe has ever approached, carrying ices that have been frozen since before the Earth had a moon, briefly warmed for the first and last time, and then sent back out into the dark on a return journey of another several million years. These are the letters that Jan Oort was reading in 1950 when he worked backward from 19 orbital trajectories to the shape of a reservoir he would never see. Every long-period comet is a letter from the outer dark. The return address is a place we have never visited, written in ice that formed before the Earth had oceans. We have been receiving these letters for all of human history, cataloguing them, naming them, reading them as prophecy, tracking their paths across the sky, and eventually learning to calculate where they came from. We only figured out the return address in 1950, and even now, knowing where the letters come from and how long they travelled to get here, There is something in looking up at a comet in the night sky that retains the quality of receiving a message from somewhere very far away. The instinct of those ancient observers was not naive. They sensed correctly that what they were seeing had come from beyond the familiar. They were just missing the full measure of how far beyond, and how long the journey had taken. The comet does not carry a description of where it came from. It only proves that somewhere out there, something sent it. What that somewhere looks like. What the sun looks like from that distance. What home looks like when you are standing at its outermost edge looking inward is a different kind of question entirely, and it has a different kind of answer. The sky is blue because of nitrogen and oxygen. That sentence is so familiar, it has almost stopped meaning anything. You learned it early enough that it feels less like a fact and more like a feature of reality. Something that was always true and always will be. A fixed property of the world, rather than a contingent outcome of specific atmospheric chemistry on a specific planet at a specific distance from a specific star. But it is a contingent outcome. The blue sky is not a universal phenomenon. It is not a solar system phenomenon. It is an Earth phenomenon, produced by the interaction of one particular star's light with one particular combination of gases surrounding one particular planet at one particular distance from that star. Move any of those variables and the sky changes. On Mars, where the atmosphere is mostly carbon dioxide and extremely thin, the sky is a pale pinkish tan, the colour of fine dust suspended in air too thin to do much with sunlight. On Venus, beneath clouds of sulfuric acid, the sky is a yellowish orange. On worlds where there is no atmosphere at all, there is no sky in any sense the word implies, stand on the surface of an Oort Cloud object. Somewhere in the outer cloud, roughly 50,000 to 100,000 astronomical units from the Sun, and look around, in every direction. Stars, not the attenuated sample of stars visible from Earth's surface, filtered through an atmosphere and washed out by scattered sunlight during the day. All of them, the full sky's worth, spread across the darkness in every direction with equal density. No horizon to cut them off. No atmosphere to dim them or make them twinkle. The Milky Way stretches in a band that here, without atmospheric scattering, is sharper and more detailed than anything visible from Earth on even the clearest night far from city lights. Individual stars are points of light without the shimmer that Earth's atmosphere produces. Steady and precise and very numerous. And in one particular direction, brighter than any of the other stars by a significant margin, is the Sun. From the outer Oort Cloud, the Sun is still the most luminous object in the sky. You could identify it without difficulty. You could point to it, but what you could not do is feel it. At 100,000 astronomical units, the Sun's energy arrives at an intensity roughly 10 billion times weaker than what reaches Earth. The warming effect is effectively zero. The surface temperature around you is not determined by the Sun at all, but by the background temperature of the universe itself, the faint remnant radiation of the Big Bang that fills all of space at about 2.7 Kelvin. You are not in the Sun's thermal environment anymore. You are in the universe's thermal environment, and the universe runs cold. At the distance of the Oort Cloud, the Sun is still sovereign by gravity, but no longer intimate by light. That sentence carries more weight the longer you sit with it. On Earth, the Sun's relationship with this planet is total in ways that are easy to underestimate because they are so constant. The Sun determines when you wake and when you sleep. Through the circadian rhythms that biology built around the day-night cycle over billions of years of evolution, it drives the weather, providing the energy that heats the atmosphere unevenly and sets air masses in motion. It powers the food chain from the bottom up, providing the energy that plants convert into the sugars that fuel almost every living thing on this planet directly or indirectly. It defines the year, the most fundamental unit of time in every human culture that has ever organized itself around anything. It makes the sky blue. It makes the seasons. It is so woven into earthly existence that dozens of human civilizations across history have worshipped it as a god, which was not naive but was simply an acknowledgement of a real and total dependency. None of that is true in the Oort Cloud. In the Oort Cloud, the Sun is an astronomical fact rather than an experienced reality. It holds objects in orbit. It is the gravitational centre of this solar system, but it does not warm anything out there. It does not light anything in any way a living organism could use. An Oort Cloud object does still rotate on its own axis, and so technically has a side oriented toward the Sun and a side facing away. But the difference in temperature between those two sides is so vanishingly small that no biological process, no chemical process, no process of any kind that we associate with life or activity could ever detect it. The concepts of day and night, of warmth and shadow, of a sky that changes as a star rises and sets, mean nothing at those distances. Everything is equally cold. Everything is equally dark. The Sun's direction is significant only as a gravitational reference, pointing toward the centre that holds everything in its slow, vast circuit. This reframes something that usually sits unchallenged at the centre of how we picture this place. We speak of the solar system as though the Sun's presence defines the whole thing, and in one sense it does, because without the Sun's gravity, none of this exists as a system at all. But the Sun's presence in the Oort Cloud is purely gravitational. It is a force without a face. It reaches across 100,000 astronomical units and holds hundreds of billions of frozen objects in slow orbits. And none of those objects experience that hold as warmth or light or the rhythm of a day. They experience it, to the extent that objects experience anything, as a constant, very gentle pull toward a direction that contains the brightest star in the sky. The solar system, as most people experience it through the things that describe it, the posters and the documentaries and the models and the diagrams, is a place organized by light and warmth. The Sun at the center, the planets bathed in its light at varying intensities, everything defined by its relationship to that central brightness. This picture is accurate for the planetary solar system. It is simply not accurate for the solar system as a whole. The solar system as a whole is mostly dark. Most of its volume receives almost no light from the Sun and no warmth at all. The bright, warm part, the part with the planets and the moons and the complex chemistry and the one known example of life, is the exception. The cold, dark part is the rule. Less than a fraction of 1% of the solar system's radial reach falls within the region that the poster shows. The rest is the Oort Cloud, cold and dark and enormous, and surrounding the bright warm centre in every direction. If there were eyes at the distance of the outer Oort Cloud, looking inward toward the Sun, they would see a star, not the star of human experience, the source of all light and heat and life on this planet, the object so central to earthly existence that whole civilizations were built around the rhythms it created. Just a star, bright and located in one particular direction in a sky full of stars, distinguished from its neighbours by its brightness and by the gravitational pull it exerts on everything nearby, but not by any warmth, not by any light that would illuminate surfaces at any useful level, not by any of the qualities that make the Sun what it is to anything alive. And around that star, invisible from that distance, too small to resolve against the background, lost in the glare of the star itself, is everything. Every mountain range and ocean basin on Earth, every city and every wilderness, every person who has ever lived, every idea that has ever changed how human beings understood themselves and their world, every moment of joy and grief and ordinary experience that has accumulated across the entire history of life on this planet, all of it circles that bright point, all of it held there by the same gravity that holds the Oort Cloud in its slow, vast orbit. From the inner solar system, the Sun feels like everything. From the outer Oort Cloud, the Sun looks like a point of light. Both of those things are simultaneously true. The sun that warms your face on a clear afternoon and the sun that is merely the brightest star in an Oort Cloud sky are the same object. The solar system that contains the blue sky Earth and the solar system that extends for 100,000 astronomical units into the cold dark are the same system. The home that feels warm and full and lit, and the home that is mostly dark and cold and vast and empty are the same home. The sun is not the center of the universe. It is not the center of the galaxy, but it is the center of this home. And from the edge of this home, it looks very small and very far, and still absolutely essential to the existence of everything that has ever mattered to anyone. On August 25th, 2012, NASA announced that Voyager 1 had crossed the heliopause and entered interstellar space. The scientists involved had been debating for months whether the data was conclusive. When they finally agreed that it was, the statement they released was measured and technical, full of precise language about plasma densities and magnetic field orientations and the specific physical measurements that indicated the crossing had occurred. The headlines were not measured or technical. Voyager has left the solar system. Humanity's probe exits solar system after 35 years. For the first time, a human-made object has left the solar system. These headlines were not wrong in the sense that they were reporting on something real. Voyager had crossed a genuine physical boundary. The heliopause is a real structure. The measurements that confirmed the crossing were solid science. But the headlines were also not precisely right, because the solar system does not have one edge. It has several, depending on which physical boundary you are measuring and what question you are trying to answer when you use the phrase solar system in the first place. The first definition is the heliospheric one. The heliosphere is the bubble of solar wind that surrounds the Sun and extends outward until the pressure of that wind equals the pressure of the interstellar medium pushing back. That boundary, the heliopause, sits at roughly 100 to 120 astronomical units from the Sun. Inside the heliosphere, the environment is dominated by the solar wind, the constant outflow of charged particles that the Sun produces as part of its normal operation. Outside it, the interstellar medium takes over. Voyager crossed that line in 2012. By the heliospheric definition, it had left, but the Sun's gravity does not stop at the heliopause, not even close. The second definition is gravitational. The solar system, by this measure, is thought to extend as far as the Sun's gravity is the dominant force acting on orbiting objects. That is a much larger region than the heliosphere. The heliosphere extends to roughly 100 to 120 astronomical units. The Sun's gravitational domain, the region where objects orbit the Sun and the Sun's gravity controls their trajectories more than any other force, extends to the Oort Cloud, somewhere between 50,000 and 100,000 astronomical units. Voyager, at roughly 160 astronomical units or more, is well outside the heliosphere but nowhere near the gravitational outer boundary. The third definition is the one most people carry without thinking of it as a definition at all. The cultural boundary, the informal one that the poster teaches, is wherever the last notable thing is. For a long time that was the last known planet. This definition has no precise physical basis, but it is the one that operates in daily life and in almost every educational context below the university level. And it is the one that produces the feeling of loss when the last item on the list is reclassified. 3 definitions. 3 different answers to the same question. The heliospheric definition puts the edge at about 100 to 120 astronomical units. The gravitational definition suggests it extends to somewhere between 50,000 and 100,000 astronomical units. The cultural definition places it somewhere between 30 and 50 astronomical units. The difference between the smallest and the largest of these answers is a factor of roughly 3,000. This is not a failure of science. It is a reflection of the fact that the solar system does not have a single natural boundary that all physically meaningful definitions converge on. Nature did not build a wall. Nature built a star and surrounded it with material under the influence of its gravity. And that gravitational influence diminishes continuously with distance, rather than stopping cleanly at any particular point. The edge is not a fence. It is a negotiation. between the gravity of the Sun, the gravity of the galaxy, and the human need for a place to put the border. Jan Oort's definition was gravitational. He proposed the Oort Cloud as the outer boundary of the solar system because it was the outermost region where objects clearly orbit the Sun on closed trajectories, returning to the Sun over timescales of millions of years rather than escaping into interstellar space. This is a physically well-motivated definition. It corresponds to something real in nature, the outermost extent of the Sun's ability to hold objects in bound orbits. But even this definition runs into a difficulty when you push on it carefully. Gravity diminishes with distance according to a precise mathematical relationship, growing weaker as the square of the distance increases. At Neptune's distance, the Sun's gravity is about 900 times weaker than it is at Earth's distance. At the inner edge of the Oort Cloud, it is roughly 1 million times weaker than at Earth. At the outer edge of the Oort Cloud, it is roughly 10 billion times weaker than at Earth, but it is never exactly zero. The Sun's gravity reaches the nearest star. It reaches, in a technical sense, every point in the observable universe, though at truly cosmic distances, other forces completely overwhelm it. The point at which the Sun's gravity becomes negligible is not a specific distance. It depends on what else is pulling on the object in question, and how you define negligible. For objects in the outer Oort Cloud, the relevant competition is the combined gravitational effect of the rest of the galaxy. All the other stars and gas and dust and dark matter whose collective pull adds up to something significant at those distances. Objects at the very outer edge of the Oort Cloud are barely bound to the Sun. A small perturbation from a passing star is enough to send them out of the solar system entirely. They are members of this system, the way a person might be said to live in a city when they actually live an hour outside it. Technically part of the system, practically on the edge of belonging somewhere else. What this means is that the outer boundary of the Oort Cloud is not a sharp line, it is a gradient. A region where the probability of an object remaining bound to the Sun over billions of years transitions from near certainty to near zero across a range of distances measured in thousands of astronomical units. There is no specific moment of crossing from inside to outside. There is a slow change from more bound to less bound to unbound, playing out over enormous distances and enormous timescales. The solar system does not end. It fades, and the fading happens so gradually, across such enormous distances, that the question of where home stops and the rest of the universe begins may not have a clean answer. Only a direction. What is out there in that directional fade? In the zone where the Sun's grip loosens and the galaxy's influence grows, is not nothing. The Oort Cloud is there, vast and cold and full of the solar system's oldest material. But the Oort Cloud itself is not immune to the forces that define its outer boundary. The very forces that eventually pull objects out of the solar system are the ones that shaped the Oort Cloud in the first place. And those forces do not come from the Sun. They come from the galaxy. Understanding that is the difference between understanding the Oort Cloud as a distant storage unit at the edge of the solar system and understanding it as what it actually is, a dynamic, permeable, galaxy-facing boundary where the solar system and the rest of the Milky Way have been in conversation for 4.5 billion years. That conversation is what the next chapter is about. On a clear night far enough from city lights, you can see the Milky Way. What you are seeing is a tiny sample of a galaxy containing somewhere between 100 billion and 400 billion stars. The Milky Way is a disk roughly 100,000 light-years across, and you are inside it, which means you cannot see its shape from the outside, any more than you can see the shape of a building from a room inside it. What you see is the combined light of billions of stars in the direction of the galactic plane, appearing as a broad, irregular band of soft light crossing the sky, brighter in some places than others, interrupted by dark lanes where clouds of dust block the more distant starlight. From Earth, this galaxy-wide gravitational system feels irrelevant to daily life. The nearest star to the Sun is about 4.25 light-years away. Its gravitational influence on the Sun, on the planets, on anything within the planetary solar system, is unmeasurably small. The other hundreds of billions of stars in the galaxy are all farther away, and their individual gravitational effects are correspondingly smaller. The galaxy is real and enormous and gravitationally complex, but from inside the planetary solar system, it might as well not exist for all the practical difference it makes to anything on or near Earth. The Oort Cloud is not inside the planetary solar system. At distances of tens of thousands of astronomical units, the Sun's gravity is weakened to a fraction of what it is at Earth. And at those distances, another force begins to matter, in a way it simply does not closer in. The combined gravitational field of all the stars, gas, dust, and dark matter in the Milky Way creates what astronomers call the galactic tide. A tide, in the astronomical sense, is a differential gravitational force. The Moon creates tides on Earth because it pulls the near side of the Earth more strongly than the far side. And that difference in pull across the diameter of the Earth distorts the oceans into the familiar rise and fall that coastal communities have organized their lives around for thousands of years. The galactic tide works by the same principle on the Oort Cloud. The galaxy pulls differently on objects at different positions within the cloud. And that difference in pull across the full extent of the Oort Cloud produces a slow, persistent force that changes orbital shapes over millions of years. The galactic tide does not rip the Oort Cloud apart. It is not strong enough for that. What it does is work quietly and continuously on the shapes of Oort Cloud orbits, in the way that water works on stone, over timescales so long that the process is invisible at any human scale but unmistakable in the results. Over millions of years, the galactic tide can raise or lower the closest approach of an Oort Cloud object's orbit. When it lowers an object's closest approach enough that the object begins to interact with the gravitational field of the giant planets, that object can eventually be nudged onto a trajectory that carries it all the way into the inner solar system. The galactic tide is one of the two main mechanisms that produce long-period comets. Some of the comets that ancient observers recorded as omens, that medieval Europeans read as signs of divine displeasure, that modern scientists study with spacecraft and spectrographs. They were sent on their inward journeys not by a passing star, but by the slow gravitational nudge of the entire Milky Way galaxy, acting on objects at the solar system's outer boundary. The galaxy has been reaching into the solar system all along. The second mechanism is more episodic. Every star in the Milky Way is orbiting the galactic center on its own path, and those paths occasionally bring other stars relatively close to the Sun. Not close in human terms. A stellar encounter might bring another star to within a light year or two, but at those distances, a passing star's gravity can significantly perturb objects in the outer Oort Cloud, sending pulses of dislodged comets inward over the millions of years following the encounter. One particular encounter is coming, and this one is close enough in time to describe with precision. The star is called Gliese 710. It is an orange dwarf, slightly less massive than the Sun, currently located about 64 light-years away. The Gaia spacecraft, a European Space Agency mission that has measured the positions and motions of over 1 billion stars with extraordinary precision, has tracked its trajectory and determined that it is heading almost directly toward the solar system. In approximately 1.3 million years, Gliese 710 will pass through the inner Oort Cloud, specifically the denser Hills cloud region closer to the Sun, at a distance of somewhere around 10,000 to 13,000 astronomical units. At that distance, well inside the denser inner portion of the Oort Cloud, its gravitational influence on objects nearby will be significant. Models suggest it could disturb enormous numbers of objects, sending waves of long-period comets inward for millions of years after the encounter. Some objects will be flung out of the solar system entirely. Others will be sent onto trajectories that eventually bring them into the inner solar system. Whatever civilization exists on Earth at that time, if any does, could eventually see an elevated rate of long-period comet arrivals continuing for millions of years. 1.3 million years is not a human timescale number. 1.3 million years ago, Homo erectus was the dominant human species on Earth. modern humans would not appear for another 800,000 years. The civilization that will exist on Earth when Gliese 710 makes its closest approach will have had more time to develop and change from what we are now than we have had from the first stone tools. Whether anyone will be in a position to look up and see the consequence of that encounter is a question that cannot be answered by any science available today. But the encounter will happen. The math is clear. The star is moving. Here is what makes this more than an interesting astronomical fact. Gliese 710 is not unusual. It is one of thousands of stellar encounters that have shaped the Oort Cloud since the solar system formed. Stars have been passing by, nudging orbits, sending comets inward, and retreating back into the galaxy for 4.5 billion years. The galactic tide has been pulling at the Oort Cloud's outermost objects for just as long. The galaxy has been involved in the solar system's internal dynamics the entire time, quietly and persistently. In a language made of gravity and measured in millions of years, the comets that cross Earth's sky are the visible evidence of this. They are the places where the galaxy's influence on the solar system's outer boundary produces something concrete and observable, and occasionally breathtaking in the solar system's bright centre. They are the messages that the interface between the solar system and the galaxy sends inward to wherever anyone happens to be watching. The Oort Cloud is where the solar system stops being alone. From Earth, the galaxy feels like a backdrop, beautiful and distant and essentially uninvolved. But at the outer edge of the sun's reach, the local rules begin to yield to larger ones. The solar system, at its extremes, is not a self-contained neighbourhood. It is a participant in a gravitational community that extends across the Milky Way, one whose membership it never chose and cannot resign from, one whose influences have been shaping the comets that cross Earth's sky since long before there was anyone on Earth to look up and wonder where they came from. We think of the solar system as our home, and it is, but home, at its furthest edges, is not separate from the rest of the universe. It is entangled with it. The galaxy reaches in, quietly and persistently, and has been reaching in since the beginning. In November of 2003, Michael Brown and his colleagues at the California Institute of Technology were scanning the outer solar system with a telescope at Palomar Observatory in Southern California when they found something that did not fit. The object was small, reddish, and very cold. Those qualities alone would not have made it remarkable. The outer solar system contains many small, reddish, cold objects. What made this one remarkable was where it was and how it was moving. Its orbit was strange in a way that took time to fully absorb. At its closest approach to the Sun, it came to about 76 astronomical units. At its farthest, its orbit carried it out to roughly 937 astronomical units. The orbital period, the time it takes to complete one trip around the Sun, is approximately 11,000 years. It was given a name, Sedna, after the Inuit goddess of the Arctic Ocean, a deity associated with the cold and the deep. The name was fitting, but the orbit was the thing that mattered. To understand why Sedna's orbit is strange, it helps to understand the gravitational geography of the outer solar system and where different populations of objects are expected to be, based on the processes that put them there. Objects in the Kuiper Belt, from about 30 to 50 astronomical units, are remnants of the outer disk, whose orbits were shaped by Neptune's gravity during the early solar system. Objects in the scattered disk, which extends from about 50 astronomical units out to a few hundred, are there because Neptune's gravity flung them onto highly elongated orbits during the period when Neptune was migrating outward to its current position. Objects in the outer Oort Cloud, beyond roughly 20,000 astronomical units, are there because the giant planets flung them so far out that passing stars and the galactic tide could then reshape their orbits into the roughly spherical distribution that Oort described. Each of these populations has a mechanism that explains how objects got there. The mechanisms are different, but they are all understood in terms of the gravitational dynamics of a solar system in which the giant planets play the dominant role in the inner regions and external perturbations dominate at the outer edge. Sedna does not fit into any of these mechanisms. At 76 astronomical units at its closest approach, Sedna is far beyond where Neptune's gravitational influence can meaningfully place objects. Neptune's ability to scatter things onto highly elliptical orbits operates most efficiently within a few hundred astronomical units at most. Sedna's orbit never brings it anywhere near Neptune. Its perihelion, that closest approach of 76 astronomical units, keeps it well outside Neptune's sphere of influence at all times. At 937 astronomical units at its farthest point, Sedna is also far too close to the Sun to have been shaped by the mechanisms that populate the outer Oort Cloud. The galactic tide and stellar perturbations become significant only at distances of several thousand astronomical units or more. At 900 astronomical units, those external forces are too weak to have produced Sedna's orbit from any reasonable starting point. Sedna sits between the two zones of influence. Too far for Neptune, too close for the galactic tide. In the region between... By the models that existed in 2003, there should be almost nothing. Objects should either have been pushed further out or remained closer in. The gap should be largely empty. Sedna was in the gap. Sedna does not sit where anything is supposed to sit. And when an object refuses to be where the map says it should be, the honest response is not to move the object. It is to ask what the map is missing. In 2012, Scott Shepard at the Carnegie Institution for Science and Chad Trujillo at the Gemini Observatory announced the discovery of another object with a similar situation. Its designation was 2012 VP113. Its closest approach to the Sun was about 80 astronomical units. Its farthest point was roughly 450 astronomical units. Like Sedna, it sat in the region between where Neptune's influence ends and where the outer Oort Cloud mechanisms begin. Like Sedna, no existing model neatly explained how it got there. Two objects in the same anomalous region started to look less like coincidence and more like a pattern. When Shepard and Trujillo analysed the orbits of Sedna, 2012 VP113, and several other distant objects that had been catalogued in the years between the two discoveries, they noticed something that made the puzzle more interesting and more difficult simultaneously. The orientations of those orbits in space were not random. They were clustered. The objects were not distributed evenly around the Sun the way you would expect from material scattered by random processes. They were bunched together in a way that suggested something might be influencing them. Something whose gravity was shaping those distant orbits into a non-random pattern. What that influence might be has been the subject of active research and genuine scientific debate ever since. One hypothesis involves the Sun's birth environment. The Sun did not form in isolation. It formed in a stellar nursery, a dense cluster of young stars born from the same collapsing molecular cloud. During the first tens of millions of years, when those sibling stars were still relatively close together, their collective gravity could have scattered objects into the gap region where Sedna now orbits, stranding them in orbits that no current solar system process would create, but that the early crowded environment could have produced naturally. When the cluster dispersed and the stars went their separate ways across the galaxy, those objects were left behind. Fossils of a time when the solar system had neighbours close enough to matter. Another hypothesis, which generated considerable attention starting around 2015, involves the possibility of a large undiscovered planet in the far outer solar system, on a very distant orbit, with enough mass to gravitationally shepherd the orbits of distant objects into the clustering pattern that Shepard and Trujillo observed. This idea has been taken seriously by some planetary scientists and more skeptically by others. As of now, no such planet has been found, despite extensive searches. The question of whether the orbital clustering is real and physically significant, or partly a product of observational bias, in which parts of the sky have been searched most thoroughly, is still being actively debated in the scientific literature. The honest answer to what is causing Sedna's orbit is that science does not yet fully know, but here is what Sedna has already established. Regardless of what eventually explains its orbit, The region between the Kuiper Belt and the outer Oort Cloud is not as empty as the models that preceded its discovery assumed. It contains objects. It may contain many objects. A substantial population of inner Oort Cloud residents that current telescopes are only beginning to have the sensitivity to detect. The surveys that will clarify this picture are ongoing. Think about what it means for Sedna to be there at all. A small frozen world, almost invisible against the dark, orbiting the Sun on a path that the best available models cannot fully account for. It was there before anyone knew to look for it. It was there before the solar system had a name. It has been there, following that strange orbit, for 4.5 billion years, in a region that the maps said should be nearly empty, carrying in its composition and its trajectory a record of something that happened in the early solar system that we have not yet fully reconstructed. Sedna is not frightening. It is not beautiful in the way a comet is beautiful. With its tail and its glow and its brief dramatic passage through the inner solar system, it is something quieter and more lasting than either of those things. It is evidence that the dark still has memory. A small red world, almost invisible, sitting in an orbit that should not exist by the simple version of the map, waiting in the cold for someone to build a telescope sensitive enough to find it and honest enough to admit that finding it raised more questions than it answered. We built the telescope. We found it. We admitted the questions. The map of the solar system is not finished. It has never been finished. Every time the instruments improve and the surveys extend further, something appears that asks a new question. And the most honest thing that can be said about the region beyond the Kuiper Belt and inside the outer Oort Cloud, the most scientifically accurate thing, is that we do not yet fully know what is out there. We know there is more than the simple map showed. We know the models were missing something real. We know that whatever is there has been shaped by forces that operated in the earliest history of the solar system, possibly including forces we are still working to understand. The outer dark has been keeping its own records. In ice and orbital mechanics, across timescales that exceed the age of any institution human beings have ever built, we are only beginning to learn to read them. On the 19th of October, 2017, an astronomer named Robert Werrick was reviewing data from the Pan-STARRS telescope system at Haleakala Observatory on Maui when he noticed something that did not belong in any catalogue he knew. The object's trajectory was hyperbolic, not just elongated. The way the orbit of a long-period comet from the Oort Cloud is elongated, hyperbolic, meaning it was not on a closed orbit around the Sun at all. It was passing through. The mathematics were unambiguous. The object had arrived from outside the solar system, was swinging around the Sun in a single pass, and would continue outward and never return. It was the first confirmed interstellar object ever detected. It was named Oumuamua, from the Hawaiian, carrying the meaning of a messenger from afar arriving first. The name turned out to be more fitting than anyone initially appreciated. Oumuamua was strange in ways that extended beyond its trajectory. Its brightness varied dramatically as it tumbled, suggesting a shape far more elongated or flat than any solar system object of comparable size. It showed a small but measurable acceleration that gravity from the Sun alone could not fully explain. It displayed no visible coma, no gas emission, none of the cometary activity that normally accompanies an icy object warming near the Sun. Scientists proposed various explanations for these peculiarities. A thin, flat object naturally formed, a fragment of frozen nitrogen from the surface of a distant world, an object with unusual composition that outgassed in ways that produced the anomalous acceleration without producing a visible coma. The scientific conversation continues. What is not in dispute is the trajectory. Oumuamua came from somewhere else. It is now gone. 2 years later, in August of 2019, an amateur astronomer named Gennady Borisov discovered a second one from his personal observatory. This object was different from Oumuamua in an important way. It was clearly a comet. It had a visible coma and a tail. It outgassed in a way consistent with an icy nucleus being warmed by solar radiation. When astronomers analysed its composition using spectroscopy, They found water, ice, and carbon monoxide and other molecules broadly similar to what solar system comets contain. Borisov was a comet from another star, likely ejected from the outer regions of another planetary system at some point in the past. It had been travelling through the galaxy for an unknown stretch of time before its path happened to carry it through ours. Its chemical similarity to solar system comets tells something worth sitting with. At least in this case, the galaxy had built something surprisingly familiar. Another planetary system, around another star, had apparently produced icy objects with chemistry close enough to our own comets that Borisov felt less like an alien object than a distant cousin, built by similar processes in a distant neighbourhood and sent wandering by whatever disruption ended its time there. Together, Oumuamua and Borisov confirmed something that had been theoretically predicted but never demonstrated. The space between stars is not empty of solid objects. It is populated by a diffuse stream of material ejected from planetary systems over billions of years. Interstellar wanderers moving through the galaxy on straight-line trajectories, occasionally passing through the gravitational territory of another star. Statistical estimates based on the detection rate of these two objects suggest that at any given moment, thousands of interstellar objects, larger than 100 meters, may be passing through the volume of space inside Neptune's orbit. Right now, passing through without stopping, carrying chemistry from other star systems into ours, and then out the other side as they continue their journey through the galaxy. The solar system is permeable, not porous in the way a sponge is porous, with physical channels through which material flows, permeable in the way that a region of space is permeable, when nothing stops objects from entering and leaving, when the boundary between inside and outside is defined by gravity rather than by any physical barrier. Objects from other stars are moving through the solar system right now. Objects that were once in our Oort Cloud are moving through the space around other stars right now, sent outward by the same perturbation mechanisms that occasionally send comets inward. The solar system exchanges material with the broader galaxy on a continuous basis, slowly and at low rates compared to what happens in the inner system. But genuinely and persistently, this changes what the Oort Cloud means. Jan Oort proposed it as a reservoir, a vast store of icy material surrounding the solar system that maintained the supply of long-period comets. That description is accurate, but a reservoir can be sealed or open. What the interstellar objects reveal is that the Oort Cloud is not a sealed tank. It is a harbour, an open harbour in a galaxy-wide ocean. Material flows in. Material flows out. The boundary between the harbour and the ocean is real, in the sense that the sun's gravity defines an inside and an outside. But the boundary does not stop traffic. It defines territory without preventing passage. Voyager 1 is part of this now. It crossed the heliopause years ago and is moving through interstellar space. At its current speed, it will reach the inner edge of the Oort Cloud in roughly 300 years and will take roughly 30,000 years to cross through it completely. When it emerges on the other side, it will be a genuine piece of interstellar material, an object that formed around the Sun and will spend the rest of its existence moving through the galaxy as a wanderer, belonging to no system in particular, heading nowhere specific. Voyager carries a golden record on which are inscribed sounds and images from Earth. Assembled by a committee in the 1970s, who knew the likelihood of anyone finding and understanding the record was vanishingly small, but believed the gesture was worth making. Greetings in 55 languages. The sounds of wind and rain and ocean waves, music from dozens of cultures, the brainwaves of a young woman in love, all of it encoded on a disk of gold-plated copper, travelling outward at 1,000,000 miles a day into a galaxy that does not know it is coming. One day, tens of thousands of years from now, Voyager will pass through the gravitational territory of another star. It will be, at that point, an interstellar object, a piece of one solar system travelling through another. It will be what Oumuamua was to us, a visitor from somewhere else, carrying the chemistry and the artifacts of a home very far away, moving through on a one-way trajectory with no ability to stop and no way to explain itself. The solar system is not a closed container. It is an open harbour in a galaxy-wide ocean, and the Oort Cloud is the shoreline where the tides of interstellar space wash in and out. We spent centuries drawing borders around the solar system, placing them at the last planet, then at the edge of the solar wind, then at the outer limit of cometary space. Each time, the universe ignored the border and kept going. The Oort Cloud is not the answer to where the solar system ends. It is the proof that the question was always more complicated than any map allowed. The harbour has always been open. The ocean has always been there. We are only now, after decades of looking, beginning to understand that we have been living on the shore all along. Find the poster again. You know the one. The sun on one side, the planets lined up in order. Everything labelled and contained. 8 planets. A neat progression from small and rocky near the centre to large and gaseous further out. Everything in its place. Everything knowable. The solar system as a diagram that fits on a single sheet of paper and can be understood by a child in an afternoon. Look at it now. After everything in the previous 14 chapters, the poster has not changed. The sun is still there. Mercury is still closest in. Earth is still third from the sun. Neptune is still at the far edge of the image. Cold and blue. The distances shown are accurate. The relative sizes are approximately correct. The ordering is right. Nothing about the physical facts depicted in that poster has been altered by anything we have covered. But you are not the same person who looked at it at the beginning. You know now that everything on that poster, every planet, every moon, every ring system, every spacecraft humanity has ever built, including Voyager 1, after nearly 50 years of continuous flight, all of it together, occupies less than 0.2% of the solar system's actual radial reach. The familiar solar system sits at the centre of a structure whose radius extends to 100,000 astronomical units. Like a coin at the centre of a room so large that the walls have never been seen from where the coin lies. You know that the room has walls. You know roughly where they are. You know that between the coin and the walls there are hundreds of billions of frozen objects orbiting the sun on paths so vast that a single orbit takes millions of years to complete. You know that those objects have been there since before the Earth had oceans, that they have witnessed without knowing it the entire history of life on this planet, that they are there right now, dark and cold and unchanged, in a silence that makes the concept of silence on Earth seem like an approximation of the real thing. You know that the walls of the room are not solid. They are permeable. Objects from other star systems pass through. Objects from our own cloud drift outward and join the stream of material that moves between the stars. The room is a harbour, and the ocean it opens onto has no far shore that any human instrument has ever seen. You know that a man named Jan Oort described all of this in 1950 from a desk in the Netherlands, using the orbital data of 19 comets, without ever seeing any of it directly. And you know that 74 years later, we still cannot see it directly, not in any photograph or image or direct observation. We know the Oort Cloud the way Oort knew it, through inference, through the shadows it casts on things that can be seen, through the comets it sends inward and the orbital patterns they leave in the data. And you know that Voyager 1, the machine that has been flying since the summer of 1977, the object that humanity sent further than anything we have ever made, is still, by the measures that matter most, very close to the coin. 300 years from reaching the beginning of the cloud, 30,000 years from crossing through it completely. Look at the poster one more time with all of that in mind. Right now, beyond Neptune, beyond the Kuiper Belt, beyond the scattered disk, beyond Sedna and all the objects like Sedna whose orbits the models have not yet fully explained, beyond the inner cloud and well into the outer shell that Jan Oort described from a desk 74 years ago. Hundreds of billions of frozen objects are moving slowly through the dark. They are not outside the solar system. They are the solar system, the part that was always too far, too cold, and too quiet to make it onto the poster. the part that has no names anyone would recognize, no photographs, no spacecraft visits planned for any time frame that any living institution is built to prepare for. They are out there right now. They were out there before you were born. They will be out there long after everything currently warm and lit and busy in the inner solar system has become something quieter. Consider where Earth actually sits in all of this. One astronomical unit from the Sun. One step in a journey whose full length is 100,000 steps. Earth is not near the edge of the solar system. Earth is very close to the center of the solar system. The edge. The gravitational boundary where the Sun's authority fades into the galaxy's background influence is equally far away, whether you look in the direction of Neptune or straight up out of the plane of the solar system or in any other direction. The Oort Cloud surrounds everything. It is above, below, ahead, behind, to every side, at the same enormous distance in every direction. We are not near the frontier. We are near the fire. The frontier is out there in the dark. At distances Voyager will not reach for centuries, across a region that no probe currently planned will enter within any time frame that current governments or institutions are built to imagine. The frontier is quiet and cold and full of the oldest material in the solar system, and it is unreachable by anything we have built or are likely to build in any future we can responsibly describe. It is ours in name, ours by gravity, ours in the sense that it belongs to the same system we inhabit. But we will not go there. The most we can do is reason our way toward it. The way Oort reasoned his way toward it in 1950, using the evidence that the frontier sends us in the form of comets that fall inward every few years from distances too great to directly observe. The solar system is not the compact neighborhood the poster described. It is a gravitational territory, mostly dark, mostly frozen, mostly silent, extending in every direction from a single warm star to distances that make the word large feel like an understatement. The planets, for all their variety and complexity, for all the geological and atmospheric richness that some of them contain, are a small bright cluster at the center of something vastly larger and vastly older and vastly quieter. And at the center of that small bright cluster, on the third planet from the Sun, on a world that has managed to be warm enough and stable enough and chemically complex enough to produce the kind of matter that asks questions about where it lives, you are here. One astronomical unit from the Sun, 100,000 astronomical units from the outer edge of home, very close to the light, very deep inside the house. Right now, Voyager 1 is moving outward at about 38,000 miles per hour. It has been moving since the summer of 1977. It will reach the inner edge of the Oort Cloud in roughly 300 years. It will cross through and emerge from the other side in roughly 30,000 years. At that point, if it survives and if its trajectory holds, it will be leaving the solar system in the deepest sense, crossing beyond the region where the Sun meaningfully holds small worlds in long-bound orbits. Nobody alive today will see that moment. It will happen in silence, unobserved, in a future so far from now that imagining it requires letting go of almost every assumption about what the world will look like when it happens. But Voyager will keep going. The physics does not require an audience, and the Oort Cloud will still be there, as it has always been there, doing what it has always done, holding the solar system's oldest material in slow orbits around a star that, from that distance, looks like just another bright point in the sky, occasionally sending a comet inward to cross the sky of whatever world happens to be watching, marking the boundary between here and everywhere else. Not with a wall, but with a gradual fading, a long diminishment of the Sun's voice against the background of 400 billion other stars. The solar system was never small. We were just born very close to the light.